dynamic. Your test one will be on the equation of motion, F equal to ma. Then question one will be F equal to ma. Question two will be work and energy, will be covered today or this week. Okay. All right. Now, for chapter 2, previously, the last tutorial question, I think example 7 or 6. The question do not include the W. The question do not put in W. In fact, the question is not properly set. It should be included the W in your calculation. So the answer that I show you in that, the set of answer that I show you in the previous lecture, we should improve the question, like ignore the weight effect. Okay, so if you follow the question, you should put in W in the free body diagram. Okay. Now today we will recap or refresh on work and energy. Okay. Let me summarize chapter 3. Basically, this one you already learned. It's just a recap of what is energy and work. Okay, work. Work is the products of force multiplied by the distance it travels. Force and distance, these two must be parallel. Force vector and the distance traveled must be parallel. Okay, the unit will be Newton meter. Okay, so as long as you see any question, you take the force, split it parallel to the surface, no matter it is slanted or what. Let's say the forces is pushing this way. You split the force parallel to the surface. Okay, you do this work, then you multiply the distance traveled, then you get work. The keyword, force and distance must be parallel. Okay. Force multiplied by perpendicular distance equals 0. No work done at a perpendicular distance. Okay. What example of work and distance that do not give you work? For example, round body. Round body is always touched at one point. The wheel and all this. If you only look at the wheel object, it's always touched at one point. The distance will be 0. Always touch at one point. Okay. Energy. Energy, you only deal with two types of energy: kinetic energy, potential energy. Kinetic, half mv square, potential mgh. Okay. Potential energy, you need to be careful on the datum. So later we explain. Something that below datum, if you start from here, you'll get negative energy, negative potential energy. When you start above the datum, you get positive potential energy. And as you see, the question asks you to use conservative of energy. Basically, energy equal, sum of energy will equal 0. There will be no loss of energy. Okay, so basically this is a summary of chapter 3. All right, we go into detail a little bit by little bit. Okay, we'll start to elaborate on the force, what is work, what is work done by the force. So let's say there is a particle moving on the curve, and you didn't see this one in statics. In dynamics, you'll see most of the time in curve. And if the force is pointing up, there's a force acting on the particles, on the object, from a reference point, this curve with a reference point from R. And because of this force, this particle move from this location to this location. So we'll form a position vector, R, dr, and R prime vector. This is the start point, this is the end point. So R prime equal to the R plus dr. You should be able to see the triangular vector. Okay, so this is the starting point, this is the end point. So we start with R prime equal to R plus dr. Okay, so we assume that we have a small changes of theta. Theta is the tail of dr and f. It is a dr vector with the force. We form a theta. So the work, we use capital U to represent work. Work done by the force will be F ds cos theta. So this is a triangular. So you split, either you split, you take the ds parallel to the force, or you take the force parallel to the distance. It's the same thing. You still get force cos theta multiplied by the ds, you get work. So the main idea here is you put the force and the distance traveled parallel, then you get work. The main idea is that, okay? So this is just a general derivation. So in this case, when you see when cos 90, when the angle between the distance and the force 90, you'll get 0. Cos 90, 0. So any force that go perpendicular to the direction of movement A or V, if the force go this way, perpendicular to the axis, then this one no work, no work done by the force. Okay. This one is okay. So this one you learn in your statics. Dot products. Vector A dot B products. You get AB cos theta. Okay, this one you learn in your statics. If you forget, you can go to my static recording in the YouTube. Go and listen to, I think, chapter 2 or chapter 3. Okay, or you can just go to Appendix B in the Canvas, go download Appendix B, go and see the dot products elaboration. Okay. So we can write the du equal to f ds cos theta also equal to dr. Okay, so this one ds cos theta also equal to dr. So this one you read. Important is that you know later you take force, go parallel with the vector distance of the distance, then you are in a good way. This one you rarely write lah. You just normally you write. Then later you integrate on. You integrate du equal to integrate f ds or dr. It depends on the setting. Okay. So these two statements here means if your force go parallel with the distance vector, vector positive, means same direction, you'll get positive work if two are parallel. So these two are vector, it's a dot products. So if one of it vector opposite of each other, it can be force, it can be distance. If it's opposite, let's say I put my force opposite with my distance, you get negative work. Okay, this is what it means. Okay, so the axis of your surface is important, and the motion of your force is important. Work will be done is only positive or negative. If the motion is moved backwards of your positive direction, then you get negative work. Or at the end, you get negative work. It means that your force is opposite from your distant axis. Means your two vector is different already. Or you can put in A dot B equal to AB cos 180. Cos 180 is -1. Unit for work will be joule or Newton meter. Newton meter or equal to joule. Okay. So in application, we will derive the equation. The total work done by the force from position 1 to position 2 will be integration of F dot dr. This is the integration steps. Because this is moving in not in the straight line, it moves in the curve or in the path that give you an equation. In statics or in a more simpler module, you will get in the straight line. In statics, you always see straight line. But in dynamic, you won't see straight line. You will see curve or very weird motion. So you apply F dr equal to cos ds. So it just means that it's just these two dr equal to cos ds. This one basically is approximate, like what you learn in the curve, theta r and s equal to r theta, assuming this one is very small angle in radian. Basically they are mean the same thing lah. It just this integration means this curve you break into small rectangular, small rectangular. Okay. This is just a rough presentation. If your force move in a straight line with the, you will form a square. Means you take force direction multiply with the distance parallel, you will get one full value. And this one you split into 90-degree perpendicular, you get 0. Okay, get 0. Okay. Later, later maybe you don't need this to remember this one. As long as you remember, every time you calculate for work, you need to put your vector force and the distance or the surface traveled by the force parallel. Then you can calculate already. Okay, you don't need to write this equation. Okay. Okay. Next, we look at different type of force. You have a force done by the weight. Done by the weight. Weight always pointing down on Earth. Right. Weight always pointing down. So the R is the direction of the position. So position 1, R1, position 2. So this is dr is a small changes along the path. So dr, you can, when you work in 3-dimensional, you can split your R vector into I, J, K. W always point down. W always point down. So W equal to -J because your Y positive go up. When you integrate work, U equal to integrate force and dr or distance traveled. So you R1 to R2, position 1 to position 2. So you integrate vector Okay. F here is the weight. Weight is minus Wj bracket dot dxi plus dyj plus dzk. Okay. Recall dot product and cross product. Dot product, you only get value when both of them go same direction. For example, I dot I, you get 1. You take I dot j, you get 0. I dot k, you get 0. Same with j dot j, j dot something, you still get 0. K dot k, you get 1. Okay. And so on. So this one you dot j dot k, j dot I, j dot I, you get 0. J dot j, you get 1. So that's why you get 1 W here. J dot k, you get 0. Okay, if you see cross, I cross I get 0. I cross j, you get something. Remember the circle of I, j, k, and anti-clockwise positive, clockwise negative. So I cross j, you get positive k. K cross I, you get positive by using right-hand rules. If this one, you use cross products. Now we are looking at dot. So it's a different products. Cross have value when two vector are perpendicular. Dot products, we have value when both go same direction or parallel. Okay. So you can integrate your W dy. So for work done by the weight will be weight multiplied by the distance traveled by the weight, but in negative direction. Okay. You only write this one when you already establish where is your positive. For example, y, x. Let's say in 2D, you have x and y, and there are some body with a weight pointing down. The work done by W will be weight multiplied by the distance traveled. But this one go down because the force go down and the distance traveled positive go up. So you get two different vector, but in the parallel line, but different direction. So you get negative value for work. Important is your reference point. So this slide only apply negative work. This slide only apply when you have a positive direction of y. Yeah. First is done by the work, by the gravitational acceleration. So this is just a pop quiz question. If the particle is displaced downward minus y, displaced downward. Okay, this one. Okay, means this one. This formula is W go down, but your displacement is go up. Means your positive direction go up is positive. So you get negative. So what if your work displaced upward? Your weight pull up already. Pull up, you go parallel with the distance, then become positive. Yeah. Okay. Just now we look at force of weight. Now we look at a spring. Because in engineering we can't avoid spring. So spring for the work is also same. When you doesn't press the spring, no work done. So when you press the spring, for example, this one you you press the spring. Work done by the spring will equal to the force with the distance traveled, for example, minus S ds, because positive X is like this one, but force go opposite of your ds. So you write du equal to minus F multiplied by ds. So these are two vectors. F is a vector, ds is a vector. So your surface vector or displacement vector is going to the right positive, but your force is placing opposite your S axis, so you get negative F there. You get a negative work. Okay. And then apply how to calculate the force to Ks. You have spring constant multiplied by the distance traveled by the spring. So you can write in the integration form, because on the top is du something, ds something. You want to get the full work done by the spring, you put in the integration sign, you'll get capital U 1 to 2 equal to negative integrate of fs ds. You pull out the k if you want, and then you integrate s. Integrate s mean s with the exponential 1. You integrate 1 will become 2 and divide by 2. If you've done the integration steps, you'll get this equation. Okay, you'll get negative continue to carry. Then you will half kx square position number 2 minus kx square position number 1. Or you can pull the constant value out, pull the half and k out. You will get s square position number 2 minus s square position number 1. Okay. So if you put the integration sign in on the chart, this black line is actually F equal to Kx. The more you pull the spring, it will going up in the linear form. F equal to Kx, when you plot Fx versus S, F equal to Mx plus C, it go through intersection 0 here. So your M is your K. So if you integrate from one location to another location, basically you are calculating the trapezium area. Okay, how to calculate trapezium? Half this one plus this one multiplied by this one, right? So if you pull your negative value here, you pull your negative, put inside here, you get positive. But anyway, you just remember this one, just in case, just in case. Okay, a mistake in sign can be avoided when I apply this equation. So note that direction of the spring force acting on the particle and compare it with the sense of direction displacement of particles. So if both are in the same sense, then positive results, means the two vector is the same, then they are positive work. If they are opposite, then negative. Okay. Let's put together what you learned in the weight and the spring together in one question. So if you have a block of the spring, support by the spring, and you are being pushed by external force of 400, so this block will go up. Spring constant is given. The surface was slanted 30 degrees. The total distance from origin, this is original position of the spring. After it released, it moved a distance of 2 meters. So this question already give you the y position and x position. You can either use this position or you can split all the forces along the axis, along the surface by using the full 2 meter if you want. Okay, because once you split the force, you can see either go perpendicular to the surface and another one goes parallel with the surface. There are two ways of solving this one. So you draw free body diagram of the blocks. So what do you feel if you are the block? You will see what? External force pushing your bodies, P. And remember to put in the weight. Remember, put in the weight. Here, it do not give you the friction. So if you don't see the friction coefficient here, you don't need to find the friction, because here also mentioned smooth. Although smooth, but there is a contact point. There's a contact normal force on the all contact surfaces. Just remember that. So I draw axis. I draw W point down most of the time from the center, from the center of the object. Pull down with a 30-degree angle from the vertical axis to the vertical axis of the object. There's a 30-degree angle. Remember the contact force. Remember the contact force, even though you don't need to calculate the friction force. There is a contact force. Every time there's a contact surface, remember. And they're always pointing towards the body, 90 degree to the surface that contact, always. Okay. Next, you have you copy the external force. The challenges is on the spring. What do you feel if you're being pushed by the spring? You're feeling the spring punching you or pulling you? Punching, right? So in this case, we just assume the spring will pull you a bit, pull you. But if you later, if you put like this, you'll find that your spring force in the, if you calculate the equilibrium of the force, you will get negative. But in this case, we will just, okay, you imagine is when at the starting, yes, you feel the spring is punching you, but as you move towards the end of this one, you'll feel that the spring actually pulling from your body. It's actually stretching from this position. Okay, so that's why the spring force. I put this one at 30 degree. So this is just a reminder. Force always go along with the distance in the same direction. So just write a general equation. Force equal work equal to force parallel direction with the distance, but you don't need to remember this one. You look for the diagram and you split this red arrow P into two directions. One is parallel, one is 90 degree go down. So 90-degree force doesn't do work. Only the one that go parallel to the distance is positive. And how you know the positive distance or surface is positive? You look at the arrow head here, tail and arrow. So positive this direction. So P and the distance are going same direction. So you get a positive from the P. There's one set of work done by the P. There's one set of work done by the spring. There's one set of work done by the gravity, W. Normal do not do work. Normal do not do work because F cos 90, 0. F cos 90, 0. Okay. So this is for the UP. You split this one into two directions. One go this way, one go this way. So we only look at the parallel direction with the surface. So 400 cos theta. Okay, 400 cos theta. Cos 30 in this case. I hope you can see the P. The P go this way. So you go this way and this way. So this P. So 30 here and here is cos. So P cos 30. This one do not generate work. You can write P sine 30, but it doesn't do work. Unless the question asks you to find acceleration, velocity, then F equal to ma, this one apply. Don't confuse chapter 3 with chapter 2 or chapter 1. This question asks you work. It doesn't ask you about acceleration or velocity. So don't confuse F equal to ma equation in this chapter. Yeah, you can say you totally forget about the acceleration and velocity. You only focus on the distance traveled by the force. Okay, the spring. The spring, you need to know what is the initial location. In this case, is let me see. So it say in the question, it say original stretch 0.5 meter. So original position is 0.5. After final position, you need to add 2 meter, 2 meter here and plus the 0.5. Okay. Means original is push in 0.5, push in 0.5 from here. So the final position actually it travel 2.5. It start from 0.5 until 2.5. So or you can say this is the before it stretch, then you, before it start experiment, it press in. You press in 0.5 here. Then after you work, then the total distance is 2.5. Then you put in the formula for spring. Work done by the spring equal to negative bracket half kx square minus half kx square, position 2 minus position 1. We substitute the value. S2 is 2.5, S1 is 0.5. Okay, maybe the diagram is not very clear. I think I agree with you that this diagram is not very good. Compared to the statement above, it might be confusing. Okay, so it might show you the 0.5 somewhere here. Somewhere here, okay? So you have the spring, and the value of the work done by the spring will be negative because the force and the displacement are opposite from each other. The spring of the force is pulling out from the body, but the distance traveled is going up. So the work done by the spring will be negative. So at the end, you substitute the value, you'll get minus 90 joule or Newton meter. Weight, again, you split your weight to two directions. One to 90 degree, one towards the downside of the slope. So you know that, and one position of W will be opposite of the distance going. So the work done by the weight will be negative. 90 degree will be 0. This purple color weight, you push 90 degree, this direction will be 0. So you take 9.81 or W equal to mg. The weight is 10 kilogram. Multiply 9.81 sine 30. Multiply 2. The weight move 2. So it's minus 98.1 Newton meter or joule. So if you compare the statement of the question, you see spring is this line, the spring is original stretch. This one might be confusing to some of you. Spring, you need to calculate the before you stretch it. This is before you start. Okay. If the question take out this line, you take out the original stretch 0.5, then in the calculation for spring just now, your S1 can put 0. This one, S1, you can put 0. S2, you can put 2. If this statement do not mention. Okay. NB, no work. This statement, write in your answer. If in your free body diagram, you have an NB, please write this statement will cost you 1 mark. If you don't write this one, maybe 25 mark. You don't write this one, you get the full answer correct. You will get 24 out of 25 because of this statement. You do not write. This one? Still, the idea still you need to put the force and the distance parallel to each other. The idea, work equal to force dot the distance traveled. Okay. NB don't have work. So total work based on your free body diagram, P do work, spring do work, W do work, NB do not do work. You add all these number together. Or you can write NB equals 0, also correct. If you're lazy to write the long sentence, you just write work NB equals 0, also correct. You add all, you get positive work 0.0500 something joule. Positive work also means as the result of resultant of everything, you sum up all everything, the object will move towards the positive displacement. Okay, this number means positive number means if you total up everything, the object will continue to move up in the positive direction, going up slope in this case. Yeah. Now we go into principle of work and energy. We start to put in energy already. We already done work, then we put in principle of work and energy. So let's say you have an object. Let's say we object moving in a curved line like this. So you know every time you see curved line, you need to mark normal and tangent direction with the particles here. And let's say you have a force. You have a resultant force pushing this way, Fr. So when there's an external force or resultant force acting on these particles, you know that you can always split your resultant force into two axes. In this case, because it's moved in a straight line, so you can push this resultant into tangent and normal direction. And this is a small distance traveled along the curve. From here, you know that normal doesn't do work. The normal do not do work because it's 90 degrees to the distance. The only do work is the tangent direction and the distance traveled along the curve. Okay, so this is just for your free body diagram work. This one, you will see you still need to write the Fn, but Fn do not do work. Okay, so this one, you just apply F equal to ma in tangent direction, F equal to ma. So ma, what is the definition? There is a definition of A equal to, when you freeze the time by instantaneous motion, you'll get A ds equal to dvd. This one from chapter 1. When you freeze the dt, you get one equation. Okay, A equal to dv dt. V equal to ds dt. You rewrite in terms of dt, both one, you'll get a ds v dv. This one from chapter 1. So you write a in terms of v and s. So a equal to v dv ds. You put inside the equation. Okay. You put inside the equation. You put this one. Put inside here. F equal to ma in tangent direction in this case. So you know that a equal to v dv ds. So you know that v, you cannot, v, you have one side, ds, you pull to another side. Ft ds equal to mv dv. So you know that ds one side, dv one side, you add integration. Okay. So you do integration sign. You pull out the mass. For the mass, you integrate v dv, you get v squared over 2. F ds, f multiplied by distance, you get work. Okay, you integrate this side, f integrate with ds, you get work. This is what you learned previously, 15 minutes ago. Left hand side, you pull out the m, you get half mv squared. Okay, so this equation is so-called, is a name, principle of work and energy. Yeah. Okay, so this one change to here. This is the equation that you need to write, but normally you write the first equation, sum of integration of ft ds equal to half mv squared minus half mv squared with the first v second minus v1. What do you think is half mv squared? Kinetic energy. So it means this one is the changes of kinetic energy. So basically, if the question forces you to use principle of work and energy, basically it asks you to write this equation or this equation. Either this one or this one. Okay, it works. So this one will cost you 1 mark. And basically it asks you, if you look at this one, principle of work on the left-hand side. So you write work on the left-hand side, energy on the right-hand side. In this case, we look at velocity. Velocity gives you kinetic energy. So this is the first one, principle, work, and energy. Just now we mentioned potential energy. Later, you need to consider potential energy, but not inside principle of work energy. You will consider under conservative of energy when you put in potential energy. So don't confuse this one. Why there's no potential energy at this moment? So principle of work energy only look at the motion and not position. Yeah, so this is principle of work energy. When we need to use this, when you need to use this formula, when the question asks you distance traveled or the force given, and you need to find the velocity after something happened. Okay, mass doesn't change, but velocity is the one that is missing. Either if the question asks you the initial velocity or the velocity after, and the work done, this one you can find from the force multiplied by the distance traveled. So either 4 parameters is missing, force missing, distance missing, velocity missing, mass will be given. So only 3 unknown here from this formula. force ds, force either force missing, distance missing. Either the question asks you what is the distance traveled by the force, or the object move, what is the distance after applying this force. So either this one missing, velocity after missing, or initial velocity missing. Then you need to use principle of work or energy to solve. Yeah. And this one in the question, if you look back all the final exam question, we will force you to use this. We'll mention very clearly by using principle of work and energy, solve something. So if the question give you, instruct you to use principle of work and energy, you go and use F equal to ma, chapter 2 question. Basically, you get 0 marks for that question, even though you get the same answer. Even though you get the same answer, because question 2, F equal to ma, you still can get the acceleration and velocity by applying the 3 Newton law, the 3 Newton motion equation. So remember, if the question mentioned principle of work energy, write this one, this equation in the question, in the answer. Or in short form, we'll use kinetic as T, capital T. Unlike work, kinetic energy always positive. Why? Even though velocity vector is negative, but you square it, you still get positive. And it's in motion. So when there's a motion, then you'll get positive. The rest is just application of what is elaborate here. So if we have you will see this one when we go into composite or rigid body later. We are now still at particles. We still look at particles, means everything sum into one centrifugal point, center of mass. So later you see in rigid body later, you need to use this equation. But at the moment, it's still sufficient to use the equation that you learned just now. Okay. So either you write this one, or you write, or T1 means kinetic equation before with the changes of work equal to kinetic energy after. So this one is what happened before equal to what after. Same, write this equation or you write this equation, same meaning. Same meaning, it's the same meaning. So kinetic energy, half mv square is the energy, so it's in joule. F multiplied by S also in joule, so everything is energy. Work is energy. What about friction? Friction do work. Friction do work because friction, it work along the distance. You know, friction is F equal to mu n. So if the question asks about friction, you need to calculate for the work for friction. Unless the question mentions smooth surface. Smooth surface, you don't need to calculate friction. So same, if you have an object that you see on the screen there, one object move from one position to another position, so it displays with the x in to the right by the force pulling from to the right. So you draw free body diagram of the box. So free body diagram have how many force? External force W, in contact with the surface, so you have a normal force. And because you are given the friction, consider the friction force, so you put in friction force. So when the question asks you to calculate principle of work and energy, you need to calculate work done by the P. In this case, in this case, perpendicular work weight doesn't do work. In this case, because it's in the flat surface, it doesn't do work. 90° down. Normal do not do work, but friction do work. So in the full equation, all the work equal to kinetic energy after minus kinetic energy after, or you can push kinetic energy before plus the change of work equal to kinetic energy after. It's the same. I forget to put in the V1 and V2. Okay, so in this case, let's say the velocity is constant, before and after is constant. So you can cancel these two. You'll get P equal to friction force. What does it mean? It means if the question mentioned the object move in a constant velocity since the beginning, then this apply. You can cancel, you write the whole equation, you can cancel the another side becomes 0 already. Kinetic energy same. Then you equal, find the unknown. Okay, so this kind of setting will usually the question will ask you to find the P required or the force required to maintain the velocity of the object by using principle of work and energy. So at first you write the principle work and energy equation, then you put in the V2 equal to V1, you cancel the right hand side, then you do the F dot ds, or you sum up all the force that created work. In this case, P create work, friction create work. Only need to be careful on the negative sign, positive sign. Wrong notation on my slides. You see the wrong notation, right? You see the wrong notation. I sub the wrong alphabet. I should not write P sub S. P multiplied by the distance, not sub. P multiplied by S become work. P sub F means force. Okay, then this one, mu K N S sub S also wrong. It should be mu N multiplied by S. So if you write like this wrong, it's a wrong notation. Okay, if you write like this, it means friction of the object S. This one, P sub X means forces acting on the subject S. Wrong notation on my slides. Okay. We complete chapter, example 2, then we go for, we only have 1 hour, right? Okay, so we go example 2, then we call it a day. Then see you on Wednesday. Okay, so you are given a automotive or car with the mass. Go down with 10°. So travel now, you know your direction or your distance already. You go down. Incline road at a speed V is given. If the driver jam on the brake, so it slow down. Cause it will to lock and determine how far the tire skid on the road. Coefficient friction is given. This one is kinetic friction, means it's in motion. It's in motion. Okay, so of course this is not a good question. The question should mention by applying principle of work and energy, find something. Okay. If this one do not mention anything, you can solve this one by F equal to ma equation. By chapter 2 equation, you can solve. Okay. So free body diagram. You draw the diagram, 10° slanted with the displacement of S towards down, from the start to down, and there's a velocity there. So you start with the weight pointing down, always pointing down. Is there any external force? No, because you're jamming brake already. You're jamming brake, so there's no pushing force. You actually slow down. So here you need to consider the normal force already, because it gives you the friction force, friction coefficient. You need to find the normal force and friction force. In this one, you sum up all the normal force in one location, in one diagram. Although you have front wheel and back wheel, normally in the particles, we only look at one point. We combine N1, N2 become 1N. Okay. Unless you see the final question, it mentioned front wheel is what? Front wheel coefficient is what? Second is what? Okay. Okay, so I go faster with it. So remember, the friction force always go opposite of the motion. So this object slide down already, so friction force will go up. You just write F sub friction A, or F friction also can, because this only have one object. Okay, I think no more forces there. You don't only need to split this one by using principle of work and energy. So what create work? W create work, because W you can split into two axes, two component. One is parallel, one is pointing down 90 degree. The one that pointing down 90 degree do not do work. The component that go parallel to the surface, slanted surface, will give you friction do work. Normal force also do work, because normal now have a 10 degree already. You can split into vertical and 30 degree. Okay, you can split this one into two direction already. Okay. Okay, normal force. Yeah, 90 degree. Normal force always 90 degree. Yeah, no. So normal A doesn't do work. Okay, the rest you read, then you calculate lah. Okay, so you do equation to equilibrium to find the NA. To find the NA, all the force in normal direction, or in the, you can put in your axis if you want, Y and X if you want. So in this case, my normal force go up positive 90 degree to the surface is equal 0. NA equal to mg cos theta. You cos it W cos theta. Then your NA equal to mg cos theta. In this case, theta equal to 10 degree. Remember to write general equation first. Don't substitute too fast. Don't jump into the value. Write equation first, then only you jump in. What's your name? What's your name? What's your name? You are in dynamic class? What's your name? Okay, you consider absent. So you solve, you get NA. You calculate friction force, you get some value. Principal work and energy. Kinetic energy 1 plus work done equal to kinetic energy 2, or you can write work equal to changes of kinetic energy, T2 minus T1, also correct. Okay. As long as you write principal work and energy, work there's a work component, there's an energy component. Okay, substitute all the value. You know T1 is half mv square. Work, in this case, you only have you have two. One is weight, one is the friction doing work. So mg, you split your mg to the along the axis, mg sine theta multiplied by the s. Okay, minus friction go opposite of the positive direction, go down. So you have a negative. So in your notes, always remember, put a star there. This will be the careless mistakes in most of the case. You will forget that friction actually is negative work. Okay, you substitute value in, you have the theta, all these things. 2 will be 0 because it's a question mentioned until stop, right? Log. So it determine how far the tire skid on the road. So means it will expect it will come down to 0. Speed becomes 0. So you do a homework, rearrange everything, you'll get the final answer 5.76 meter. Okay, so this is the focus of today. What is the principal work of energy? There's a work component, there's a kinetic energy component. What is work? Work, as long as the force multiplied by the distance traveled, you get work, and must be go parallel to get positive. If one of the vector go opposite of each other, you get negative work. And then there's an equation for spring, work done by the spring, work done by the weight. This one you can read from your free body diagram, doesn't matter. I think the spring is another extra mouse that you need to go and remember. Yeah, so that's it. So I also cover example 2 with chapter 2 answer. You can solve by F equal to MA if you want, you get the same answer. Okay. Ah, 没问题，没问题，没问题。你看回去，就你看回去那个 recorded video 就可以了。啊。好的，没问题，没问题。回去看那个 video 了。